Hey y'all, how you doing? Hope you're having a great day. Today we're going to continue our discussion on how light absorption occurs. This is part 2 to a 3-part series. In this part we're going to cover the damped harmonic oscillator. So, a review of the first part. First we considered a neutral part of space, which actually was a positive charge overlapped with a negative charge, and then we applied an electric field, and after some time those charges are going to separate into something like this, separated by a distance d, and we considered what happens if you turn on the electric field, the charges separate, and then immediately you turn it off. Well, these charges are going to oscillate back and forth like a simple harmonic oscillator. But there's one thing we did not consider, which was the effects of dampening. So just like in everyday life, there's forces due to friction and other forces that'll dissipate the energy of the oscillator. So eventually this thing's going to be set in motion and oscillate, but it's going to decay back to its equilibrium position. And today we're going to consider those dissipative forces. So, the equation we saw last time for the simple harmonic oscillator was that it obeys this equation, that the second time derivative of the position plus the frequency squared times the position equals 0. And we saw that our solution we could write as x of t is equal to some constant a times the imaginary exponent e to the I omega t. Or we could rewrite this using trig identities and Euler's formula as another constant b times sine omega t plus phi, where phi is a phase factor. Or we could even write it as c times cosine omega t plus phi. And we can even rewrite the exponential and add the phase factor in there too if we want. These all satisfy that equation. Now today what we're going to add is an extra force. So usually in everyday life you can think of dissipative forces as such as drag on your car. So when you're driving your car down the road, air is hitting your car and so if you just push the gas and let go of the gas, eventually your car is going to slow down and stop. That's because the drag from air. And the faster you go, the greater the drag force is going to be. So we can write that as F, the force, we'll call it the F sub damp, the dampening force, is equal to minus the damping coefficient times the velocity, or we'll rewrite the velocity as the derivative of the position with respect to time. And in part 1, we said that the force, the restoring force, just follows Hooke's law. It's negative kx, where k is the spring constant, or basically how stiff your spring is, or how strong your bond between charges may be. That's what k is. And then Newton's second law tells us that the total forces equal the sum of both of these, so it equals the damping force plus the restoring force. So that just equals negative gamma dx dt minus kx. And that all equals the mass times the acceleration, or the mass times the second derivative of the position with respect to time. Now we add both of these terms to that side, and we get that the mass times the second derivative of the position with respect to time plus gamma dx dt plus kx equals 0. And we can divide through by m, and we get this, plus gamma over m dx dt plus k over m x equals 0. We're going to rename these constant just so we don't have to keep writing the over m part. We're going to call gamma over m, let's call that this other gamma term, the one that I have a lot of trouble writing, but it's also called gamma. And we're going to write k over m is equal to omega squared. So then our equation would read the second derivative of its position with respect to time plus gamma dx dt plus omega squared x equals 0. Now this is the differential equation that we want to solve here. This is the differential equation for the damped harmonic oscillator. Notice this is our simple harmonic oscillator equation, and we can get this from this when we set gamma equal to 0, or if there's no damping, we get the simple harmonic oscillator. So to solve this, we go to the mathematicians and be like, hey, how do you solve this differential equation? And they're like, oh, that's a piece of cake. That's a second order linear differential equation with constant coefficients. And the general solution for that is x of t is equal to some constant c1 times e to the r1t plus another constant c2 e to the r2t, where r1 satisfies this is called like the characteristic equation or something like that. But you plug this in, and well, the constant out here would be a, and this would be b and c. They would write it like, but our a is equal to 1, our b is equal to gamma, our c is equal to omega squared. Okay, so you would use the quadratic formula. It says negative gamma plus or minus, but the r2 is the minus part, square root of gamma squared minus 4a, our a is 1, c, our c is omega squared. Yes. All over 2a. All over 2, our a is 1. And then r2 is going to be the same thing, except we're going to put the minus sign there instead of plus. It's 4 omega squared over 2m. So that's what the mathematicians would tell you. That's how they tell you to solve this. It's the most general solution. Well, from this we see that we have three cases. We have three cases. Case 1, gamma minus 4 omega squared is greater than 0. Case 2, gamma minus 4 omega squared is equal to 0. Case 3, gamma minus 4 omega squared is less than 0. So now we're going to go through each of these three cases and see the result that we end up with. So I'll flip to the next page, and we're going to begin with the first case. So, first case, it was gamma squared minus 4 omega squared is greater than 0. Well, this is the easiest case. Let's rename some things. Let's call, since we have the square root of this thing, we have the square root of gamma minus 4 omega squared. Let's call that alpha, just so we don't have to keep writing that. And our general equation said x of t equals c1 e to the r1t plus c2 e to the r2t. Now notice alpha, it's always going to be less than gamma, and that is because here we're taking gamma squared, but we're taking the square root of that. So that's going to be at least equal, well, that would be equal to gamma, but we have this term here, the omega is always positive, so you're effectively making this less than gamma squared, and then you're taking the square root of that. So therefore, alpha is always less than gamma, and our R1 and our R2 is going to be negative. So if we recall, we said R1 is equal to negative gamma, this other gamma, plus alpha over 2. And R2 is equal to minus gamma minus alpha over 2. So our equation now reads C1 e to the R1, so minus gamma over 2 times t, and then plus alpha over 2t plus C2 e to the negative gamma over 2t minus alpha over 2t. And you can rewrite this also as okay. So that's our equation for case number 1. This case is called overdamping. And overdamping basically means that your force constant K is so large, because remember, omega squared was equal to the square root of K, no, it was equal to K over M. So if K is very, very large, then effectively this term will be pretty close to gamma, but it's basically saying the two things that are oscillating are so strongly bound that they don't really want to oscillate. They just want to return to their equilibrium position. So you can think of this kind of like if you try to punch a solid object, that object's not going to oscillate. It's going to be like, nope, I'm staying at my equilibrium position. So if we plot this first time, it's essentially an exponential decay. The larger the gamma is, the faster it'll decay to 0. There's not really any oscillation in this case. And I would say this is probably the least interesting case. Anyways, let's go to case 2, where we said gamma squared minus 4 omega squared is equal to 0. Well then, our solution is going to be x of t equals a plus bt e to the negative gamma t over 2. And I won't go into the details of why this is, but that's the solution to this case. And this case is called critical dampening. And this is effectively like when you try to bend something that's not very flexible, or I guess it could be flexible, but you bend it and it slowly returns back to equilibrium position. So if I try to bend the object like I try to bend my pencil, it's, let's say this is the equilibrium position, and then I bend it out of its equilibrium position, it's going to slowly return back to the equilibrium. It's not going to go like straight to it, and it's not going to oscillate back and forth. It's just going to slowly go back to it. In this case is critical dampening. And this case is a little more interesting because engineers try to match this critical dampening condition you can see the condition. You have to make the damping coefficient equal to 4 times the square of the frequency. It's good for engineering purposes, but I'm not an engineer, so I can't really tell you that much about it. Let's get to the most interesting case, which is case 3. And in this case, gamma squared minus 4 omega squared is less than 0. So, we can rewrite gamma squared minus 4 omega squared as equal to negative 1 times 4 omega squared minus gamma squared. All I did was pull a minus 1 out. So if we do that, we can rewrite the square root of gamma squared minus 4 omega squared as negative 1 times 4 omega squared minus gamma squared. But the square root of negative 1 is just I, so we got I times the square root of 4 omega squared minus gamma squared. And now we rewrite this in terms of our r's, so our r1 is going to be negative gamma plus, let's call this, what should we call it? Let's call it beta. We already used alpha, so let's use beta. So plus I beta over 2. R2 is going to be equal to negative gamma minus I beta over 2. And then so our general solution for this case is going to be C1 e to the R1t, so R1 is negative gamma plus IB over 2, all that times t plus C2 e negative gamma minus I beta over 2, all that times t. Okay, well now we can rewrite these exponentials. And I can pull this exponential term out. And now what I'm going to do, since we have e to the I times something, I'm going to use Euler's formula, which says that e to the ix equals cosine x plus I sine x. I'm going to use this formula to rewrite this term in parentheses in terms of sines and cosines. Okay, so all I did there was use Euler's formula to write these complex exponentials in terms of sines and cosines, and I renamed the constant coefficients capital A and capital B. And we can rewrite this again using trig identities, which I will not do here, but I will show how we can rewrite this on the next page. So, just for reference, on the previous page we wrote that's what we wrote on the previous page, and using trig identities we can get that so we can get here from here, and we can get our omega back, and our phi will be a parameter that depends on the damping coefficient and the frequency and various sorts of things. But you're just going to have to believe me for that. I'll leave that to yourself to use trig identities to get from here to here. And this c is also another constant. Now this is the most important case, and this case is called underdamping. And this resembles everyday phenomenon, so many things in everyday. It resembles if you pluck a guitar string, the guitar string's gonna resonantly vibrate, but eventually decay. The same thing with a tuning fork. The same thing with a pendulum. The same thing with a child on a swing. All these things are gonna go through multiple oscillations like this, but the oscillations are eventually going to decay down to 0, where here I have x of t on this axis, this axis, okay, this axis, I have t. So, I hope that was helpful. This is our main result. This is definitely the most important case. And we're going to be seeing this again. Now I'm going to turn it over to Mathematica so we can look at the behavior of the functions in each case and see how the functions change as we change the parameters, such as the damping coefficient and the natural resonant frequency, which is omega. I've been calling it the frequency, but it's actually, I should have been calling it the resonant frequency of the material. It's a property of the material. So is the damping coefficient. So, yeah, I'll turn it over to Mathematica from here. I think I'm just going to make it a supplementary video. So, if you don't want to watch that video, thanks for watching this one. Hope you enjoyed it, and have a great day.